Hey guys, this is Professor Janacek. Want to go over a convergence test. Want to specifically look at the ratio test. We're going to look at a general series. Want to point out that the terms of this series must be greater than 0. Now I'm not going to go over why the ratio test works, just want to go over how to use it. We'll begin by taking the limit as k goes to infinity of the absolute value of a sub k plus 1 over a sub k. If that limit is less than 0, then our series converges. If that limit is less than 1, the series converges. If the limit is greater than 1, the series diverges. But if that limit is equal to 1, then this test is inconclusive and we'll have to try another test. All right, let's dive right in and take a look at some examples so we can see how this works. Let's start with the sum as k goes from 1 to infinity of k squared over 2k minus 1 factorial. Let's consider that limit as k goes to infinity of, in the numerator we're going to look at the k plus 1 term, so anywhere there's a k, I'm going to write k plus 1. So we have k plus 1 quantity squared over 2 times k plus 1 minus 1. That quantity is factorial. In the denominator, I leave the terms as is, k squared over 2k minus 1 factorial. All right, let's simplify some stuff before we take this limit. First thing we'll do, let's see, I'm going to multiply by the reciprocal to clear that complex fraction. I'm also going to go ahead and take this 2, we'll distribute it and combine it with that negative 1. So simplify a few things there in that factorial in the numerator. So we have k plus 1 quantity squared over 2k. Distribute out the 2, we get 2 minus 1, so that's 2k plus 1 factorial. Multiply by the reciprocal, we have the 2k minus 1 factorial in the numerator, and k squared is now in the denominator. All right, next thing I want to do, I recognize that this 2k plus 1 factorial is a larger term than the 2k minus 1, so I'm going to write out a few terms there in that bottom one. Maybe I'll be able to reduce some stuff. Also, while I'm at it, let me go ahead, actually I'll just start there. Let's just do that, and then we'll one step at a time here. So the numerator, going to leave alone for now, but 2k plus 1, I recognize that's 2k plus 1 times 2k times 2k minus 1. Those are the first three terms. I'll leave the factorial on the last term. So that last term includes all of the terms below it. I recognize that I can reduce those. Along with reducing those, I'm also going to expand the binomial in the numerator, and I'll go ahead and take the 2k and the k squared and distribute those into that binomial in the denominator. All right, so we have the limit as k goes to infinity. Again, squaring that binomial, k plus 1 squared gives us k squared plus 2k plus 1. The 2k minus 1 factorial cancels out. In the denominator, 2k times k squared is k cubed. Distribute that into the 2k plus 1 gives us 4k to the 4th plus 2k cubed. All right, now we're going to do one more thing before we take this limit. I need to kind of get it in a form where I could easily take the limit. I'm not going to use L'Hopital's rule. Instead, I'm going to use this little technique whenever we have a rational expression, polynomial in the numerator, polynomial in the denominator. Take a look at the highest degree in the denominator. Multiply in this case by 1 over k to the 4th in both the numerator and denominator. I put that in absolute values, which is fine because my k's are getting really large in the positive direction. So attaching a absolute value is not going to cause any problems with that. If we distribute the 1 over k to the 4th in there, we end up with the limit as k goes to infinity of the absolute value of 1 over k squared plus 2 over k cubed plus 1 over k to the 4th over 4 plus 2 over k. I think now we're ready to take that limit, so we're looking at k getting really large. In that case, all of these little fractions will all go to 0. So we end up with no limit notation, ready to take the limit 0 plus 0 plus 0 over 4 plus 0. Absolute value of that, we end up with just 0 over 4, which is 0. Notice this is defined. I don't have 0 in the denominator. That's good. But the other thing I notice is that this is less than 1. And since this limit is less than 1, our series converges. All right, that wasn't so bad. Let's try another. Let's take a look at the sum as k goes from 1 to infinity. I'm sorry, let's start this one at 0 to infinity. And our series looks like k factorial over 5 to the k. Now because we're starting at 0, I do need to check what's going on at 0, evaluate this for the 0 term. That's 0 factorial over 5 to the 0 plus the sum as k goes from 1 to infinity of k factorial over 5 to the k. Well, 0 factorial is 1 over 1. So we end up with just 1 plus the sum as k goes from 1 to infinity of k factorial over 5 to the k. All right, so that plus 1 isn't going to really make too much of a problem. We'll add that on to whatever our answer is at the end. So now let us just consider the limit as k goes to infinity of the absolute value. Now again, I'm going to be looking at my a sub k terms there. I'm going to add 1 to all of those k's. So in the numerator, we have k plus 1 factorial over 5 raised to the k plus 1. In the denominator, I leave those terms as is, k factorial over 5 to the k. All right, let's go ahead and multiply by the reciprocal here. We have k plus 1 factorial over 5 raised to the k plus 1 times 5 to the k over k factorial. All right, a couple things I want to do. I'm going to write out a couple of terms for the k plus 1 factorial. I'm also going to go ahead and rewrite this 5 raised to the k plus 1. We can rewrite that using our properties of exponents. So our terms now become, let's see, we've got k plus 1 times simply k factorial. We still have 5 to the k there in the numerator. In the denominator, we have 5 to the k times 5 to the 1, which is really just 5. And then we still have the k factorial. I see I can reduce some stuff. We'll reduce the k factorials. We'll reduce 5 to the k. All right, that's going to simplify things quite a bit. So now we have the limit of the absolute value of k plus 1 over 5. And I think we're about ready to take that limit. There's not a lot we can do with this. As k gets really large, k plus 1 also gets really large. So this whole thing goes to infinity. Now, if you remember our original series had that plus 1, so it turns out we're going to add 1 to infinity. That's still really large. In either case, that limit would be definitely greater than 1. And if that limit is greater than 1, it diverges. Again, so what we've just determined is that this bit diverges, meaning we have 1 plus something that diverges, which means what we end up with is something that diverges. All right, not so bad. Enjoy.